Hi, welcome back to educator.com. Today we're going to talk about partial fractions. Consider if we had two quotients of polynomials that we wanted to add together, like say 7 over x minus 5 and 3 over x plus 2. We could put them over a common denominator, then combine them, right? We've got x minus 5 here and x plus 2 here, so we can multiply the one on the left by x plus 2. So we get x minus 5 over x minus 5 times x plus 2 on the bottom, so its top will get also multiplied by that x plus 2. For the other one, we'll have x minus 5 multiplied on it, so it has x minus 5 multiplied on the top, so we've got x minus 5 times x plus 2, common denominator on the bottom now. We multiply those out, we get 7x plus 14, 3x minus 15. We combine those, we get 10x minus 1 on top, divided by x minus 5 times x plus 2 expanded to x squared minus 3x minus 10. So not a bad idea, right? We can get from here to here by putting it over a common denominator and then just adding things out and simplifying. But what if we wanted to do the reverse process, right? What if we started with a fraction involving large polynomials and we wanted to break it into smaller fractions made of the polynomial's factors? If we want to do this process in reverse, if we started at 10x minus 1 over x squared minus 3x minus 10, and we somehow wanted to be able to get that into 7 over x minus 5 and 3 over x plus 2, what process could we go through? We call the smaller fractions on the right partial fractions because they are parts of that larger fraction. So each of these guys here, 7 over x minus 5, 3 over x plus 2, they're each called a partial fraction, and the process to break it up is called partial fraction decomposition. So whatever this method is that we haven't explored yet, to get from that larger polynomial quotient into these smaller partial fractions is called partial fraction decomposition. So how do we do it? To understand this lesson, to understand how we do it, you'll need some familiarity with solving systems of linear equations. Previous experience from past algebra classes will probably be enough to get through this, but if you want a refresher, if you're a little confused about how this stuff is working later on, check out the lesson Systems of Linear Equations. That'll help explain this stuff if it confuses you right now. You'll also need to know how to factor polynomials, and you'll need to understand them in general, along with the ability to do polynomial division. So you'll need all that under your belt for some of the stuff in here as well. Now, sadly, we won't be able to see the application of partial fraction decomposition in this course. However, it is quite useful in calculus, where it will allow us to solve otherwise impossible problems. Partial fraction decomposition is this really useful thing that lets us break up these complicated things that we couldn't solve and turn them into a form that is actually pretty easy to solve. So it's really handy in calculus. We won't be able to see its use in this course. We won't see it anytime soon, but it's helpful to practice it now. Just like we practiced stuff about factoring complicated polynomials in algebra before we really had a great understanding of what it was all about, we're practicing something so that we can use it down the road. And also it just is a great chance to flex our brain and get some cool mental muscles that are kind of difficult ideas but really require some analytic thought. All right. Let's get to actually figuring out how to do this. If we have a polynomial fraction in the form numerator polynomial divided by denominator polynomial, a normal rational function format, there are two possibilities in regards to the degrees of the top and bottom polynomials. We call them proper. Proper is when the degree of the numerator polynomial is less than the degree of the denominator polynomial. So the degree of n is less than degree of denominator. And improper, when the degree of our numerator is greater than or equal to the degree of our denominator. To decompose the fraction, it must be proper. We have to be in this proper format. So we have to make sure that the degree of our numerator is less than the degree of our denominator if we want to do partial fraction decomposition. So what do we do if the fraction is improper? We've got to turn it into a proper thing. So if the fraction is improper and we want to decompose it, we have to make it proper through polynomial division. We can make that numerator smaller by being able to break it off and divide out the part that isn't smaller and the part that is smaller. So remember, when you divide through polynomial division, the remainder from the division goes back onto our original denominator, which we will then decompose. We'll be able to decompose the part that is the remainder. The other part that comes out cleanly, well, that's just going to be there. That's just going to be a polynomial that is then going to be added to whatever winds up coming out of our decomposition. We'll see an example of this in example 3. Once we have a proper polynomial fraction to decompose into partial fractions, remember proper, our numerator has to be smaller than our denominator before we can enact this process. Once we've done that, we can then factor the denominator. Our next step is to factor the denominator. After the denominator is broken into its smallest possible factors, we're ready to decompose. Now there's two types that these smallest possible factors can come in. They can come in linear factors, which is forms ax plus b, and they'll be raised to some power because we might have multiplicity of these factors. There might be multiple of a given factor. So if we have multiple ax plus b's, we'll have m of them, so ax plus b to the m. So we'll have linear factors in this. Or we could have irreducible quadratic factors, that is things ax squared plus bx plus c that can't be broken up further into linear factors. There's no way to break them up further in the reals. So ax squared plus bx plus c, and once again it will be raised to some power, so there will be m of them, so it's raised to the m, because there's m of them multiplied together. Remember, irreducible means it can't be broken up further in the reals. That means quadratics like x squared plus 1 or 5x squared minus 3x plus 20, because they have no roots, right? X squared plus 1 has no roots. X squared plus 1 equals 0. There's no solutions, right? No solutions in the reals, at least. If we allow for the complex, there are, but we're not working with the complex. So there's no solutions in the reals. So since there's no solutions in the reals, it can't be factored any further. X squared plus 1 is irreducible, therefore. The next step of decomposition will behave differently depending on which flavor of factor we have, whether we're at a linear factor or we're at an irreducible factor, and we'll look at the two one after another. Linear factors. The partial fraction decomposition must include the following for each linear factor that is in this form ax plus b to the m. So it's going to have this in its decomposition: a1 divided by ax plus b plus a2 over ax plus b squared plus, notice that we're doing this where it's going to keep stepping up with this exponent on the bottom as we keep putting these things until eventually we get up to our mth step, because we had m of them to begin with, so we have to have m of them in the end. And each one of these a's on top, a1 up until am, are all just constant real numbers. So we're using a with subscript, this a1, a2, a3 business, because we just need a way of being able to say m of them, and we're not quite sure that we're going to go only out to n. Anyway, so point is they're all going to be constant real numbers. For example, if we had x plus 7 cubed, then we've got some stuff up top. We don't really care what the stuff is right now because we just want to see how it will break out. We'll deal with the stuff later. So if we have stuff over x plus 7 cubed, then it's going to break into 3 of these guys because of this cubed. So we'll have a over x plus 7 plus b. We can switch into just using letters in general because we know that each one of these capital letters just means some constant real number. We'll figure them out later. That'll come up later, don't worry. A over x plus 7 plus b over x plus 7 squared plus c over x plus 7 cubed. Notice, we started cubed, and so we have 3 of these. We step up each time with the exponent until we've gotten to the number of our multiplicity that we originally started with, whatever the exponent was originally on the factor. If we've got multiple linear factors, we do it for each one of these. So if we've got 2x plus 3 squared, x to the 1, since there's nothing there, x minus 5 to the 1, since there's nothing there, we've got a over 2x plus 3 plus b over 2x plus 3 squared, because remember it was squared to begin with, so it has to have 2 of itself, plus c over x, and there's only to the 1, so there's only going to be 1 of it, plus d over x minus 5. And it's only 1 because there's only 1 of them to begin with. And each one of these a, b, c, d, they're each just constant numbers. We're going to figure them out later on. Don't worry. Irreducible quadratic factors. The method's very similar for irreducible quadratic factors. The decomposition must include the following for each irreducible quadratic: ax squared plus bx plus c to the m. Once again, the same thing of stepping out m times. So a1x plus b1 over ax squared plus bx plus c. Notice how previously it was a over some x plus, constant, because we had the degree of the top is 1 below the degree on the bottom. So the degree on the top here, it's a linear factor on top because we've got a quadratic factor on the bottom. Previously, we had a constant factor on top because we had a linear factor on the bottom. So a1x plus b1 plus a2x plus b2 over, that should be a capital, whoops, over ax squared plus bx plus c, now squared, because we're doing our second step. And we do this out m steps until we are at our m constants, and we are at the mth exponent on the bottom. So a1, all these capital letters, b1 to bm, they're all just constants, and we'll figure them out later. For example, if we had x squared minus 4x plus 5 squared on our bottom, then we've got some stuff, doesn't really matter right now, x squared minus 4x plus 5 squared, so we're going to have this happen twice. First one will be just to the 1, second time it will be squared, and on the top it's going to be ax plus b and cx plus d. So a, b, c, d, these are all just constants, we'll deal with them later. If we have multiple irreducible quadratics, we just do each of these. So for example, if we had x squared plus 2x plus 3, that is an irreducible, and x squared plus 4, and it had squared, then we have ax plus b, x squared plus 2x plus 3. There's only one of them, so it only shows up once, plus cx plus d over x squared plus 4. It's going to show up twice because of that 2, so it shows up a second time here. And so we've got ex plus f. So we just keep doing this process of, capital letter x plus capital letter x plus capital letter until we worked out all of the times that we had things showing up, right? Total of 3 because we had 1 there and 2 there, so total of 3. If we've got both types, a linear and an irreducible quadratic mixed together in the denominator, that's okay, perfectly fine. We just decompose based on both of the rules. So for example, if we had x plus 9 squared, then the x plus 9s are going to follow this this single constant format, because linears just had one constant on the top, x plus 9, and then x plus 9 squared. And then we switch to the other rule, x squared plus 1. Now we're dealing with an irreducible quadratic, so x squared plus 1, and we've got cx plus d on top, because we've got to be able to have, since we've got a quadratic on the bottom, we've now got linear factors on the top. When we're dealing with linear factors on the bottom, even if it's multiple linear factors, it's just constants on the top. All right, now finally, how do we figure out what those numerators are? We've mentioned that the numerators are built out of constants. Remember, a for linear factors, constants for linear factors, bx plus c, linear factors for irreducible quadratic factors. But we haven't talked about how we actually find out what these capital letters values are. We solve for the constants by doing partial fraction decomposition. So we set them up in this format, and then we multiply each side of the equation by the original denominator. It'll make more sense as we work through examples. Let's look at this example. If we had 3x squared plus 3x minus 4 divided by quantity x plus 3, one factor, times quantity x squared minus x plus 2, an irreducible quadratic factor, then we'd be able to break it into a over x plus 3, right? X plus 3, a over x plus 3, so we get this right here. And x squared minus x plus 2 would be bx plus c, x squared minus x plus 2. So we know from what we just talked about, this process that we just went through, that's how it breaks up. But how do we figure out what a and bx plus c are? Well, notice, we can just work things out the way we would a normal algebra thing. We multiply both sides because we want to get rid of this denominator. We'll multiply by x plus 3 on the left side and x squared minus x plus 2 on both sides. So we do the same thing on this side as well. So x plus 3, we'll color code this guy, x plus 3, and x squared minus x plus 2. So the x plus 3 will distribute to the guy on the left and the guy on the right. It has to hit both of them because it's distributed, because there's this plus sign right here. So x plus 3 will distribute to both of them. Similarly, x squared minus x plus 2 will distribute to both of these as well. Now, notice on the left side, we've got x plus 3 on the bottom and multiplying by x plus 3. So x plus 3's, boom, they cancel out. X squared minus x plus 2, right here and here, boom, they cancel out. What about on the left side? Well, we've got x plus 3, x plus 3. So here, it's going to cancel this and this, but it will still have the x squared minus x plus 2 coming through. What about bx plus c over x squared minus x plus 2? Well, x plus 3 is still going to come through. Doesn't cancel out any factors here, but x squared minus x plus 2, that's the same thing, so it will cancel out that part of the factor coming in. So we will see that we've got a times x squared minus x plus 2 and bx plus c times x plus 3 coming through, right? This part right here manages to come through on the bx plus c, and this part right here manages to come through on the a. And on the left, since we canceled out everything on the bottom, we've just got what we had on our numerator originally. That just makes its way down. So we've got 3x squared plus 3x minus 4 equals a times x squared minus x plus 2 plus bx plus c times x plus 3, which we can then expand everything on the right, and we can work things out by creating a system of linear equations. The examples are going to help greatly in clarifying how this works, so check them out, because we'll actually see how this process of setting up our system of linear equation works and solving for what these values are in each of these examples. Not example 2, but we'll see it in a lot of the examples, and it will make a whole lot more sense as we see it in practice. So let's go check it out. All right, first example, nice simple example to get things started off with. Find the partial fraction decomposition for 4x plus 3 over x times x plus 3. So we have 4x plus 3 over x times x plus 3. Now that's going to be equal to, we've got two linear factors on the bottom, so a over x plus our other linear factor, b over x plus 3. Now at this point, we can multiply everything by x and x plus 3. Multiply everything by x and x plus 3. Great. So on the left side, that's just going to cancel this stuff out. And on the right side, it will wind up distributing. So on the left side, we've got 4x plus 3 equals a. Now notice, we've got the x multiplying here. That's going to cancel out. So the x's parts get canceled out, but we're left with x plus 3 multiplying on it, plus b times x plus 3. So the x plus 3 part cancels out. I'll switch colors here. So x gets through, but the x plus 3 cancels out the denominator. Great. So we've managed to get rid of all of our denominators. That's great. Make things easier to see what's going on. And we've got some stuff multiplied through. So at this point, 4x plus 3 on the left equals ax plus 3a plus bx. Now notice, we see here that we've got a 3 constant. Now, what constants do we have on the right side, right? We've got to have all of our x's match up, all of our constants match up. Well, the only thing that's actually a constant on the right side is this 3a, because we've got ax and bx, but we don't have any b just as b. We don't have any constants of b. So it must be that 3 and 3a are equal because they're all of the constants that show up on either side of our equation, right? The same thing has to be on the left and the right, otherwise it's not an equation. So that tells us that 3 equals 3a. So what's our a? We divide both sides by 3. We get 1 equals a. So now we've figured out what a is. What about the other part? Well, we've got that 4x is equal to, let's give it a special thing, so we'll give it a curly around it. So 4x is equal to all of our x's on the right side put together. So that is our ax combined with our bx. So it must be the case that 4x is equal to ax plus bx, because our x's, the same number of x's, must be on the right side as on the left side. So 4x must equal ax plus bx, because these are our sources of x on the right side. So 4x equals ax plus bx. Hey, we just figured out what a is, so we can plug that in over here. So we've got 4x equals ax plus bx. Now notice, actually before we do that even, we've got 4x equals ax plus bx. So if that's the case, let's just get rid of these x's, right? We know that it must be the case that since 4x equals ax plus bx, well, those x's, that has to be true for any x that we plug in at all. So it must be the case that 4 equals a plus b. We can divide x out on both sides, and we cancel that to 4 equals a plus b. So 4 equals a plus b. Now we can substitute in that 1. It'll make it even clearer what's going on. 4 equals 1 plus b. Subtract the 1, we get 3 equals b. So at this point, we've figured out what a is. We've figured out what b is. So we see we can now go back to our partial fraction decomposition. We can plug in actual numbers, and we can have what that is equivalent to. And we've got 1 over x plus 3 over x plus 3. And there's our answer. Great. All right, next one. Write out the form of the partial fraction decomposition, but do not solve for the constant. That's good, because this will be a doozy if we actually had to solve it. So first we've got x, and then x minus 7 squared, and then 2x squared plus 1, an irreducible quadratic, cubed. All right, so we've got a over x plus, next one is a linear, so it's also just one constant up top, x minus 7, but it's squared in our original thing, so it gets squared. So another constant, c over x minus 7, this time 2 of them, multiplicity 2 squared, plus dx plus e, because now we're dealing with an irreducible quadratic. First time it showed up, so 2x squared plus 1, plus fg, so fx, just keep going with letters. I'm just counting off the alphabet at this point. Fx plus g, a, b, c, d, e, f, g. Don't want to screw up my alphabet. 2x squared plus 1. Now we're at the second time, so squared hx plus I over 2x squared plus 1 cubed. And that's the partial fraction decomposition. We haven't figured out what A, B, C, D, E, F, G, H, I are, but we could if we multiplied, because we know that this thing here is equal to this thing here once we get those correct constants in. So we could multiply the left side and the right side by that denominator, and everything would cancel out and we'd be left with this awful, awful mass of things, but we could solve it out slowly but surely. Luckily, all it asked for was to just set things up, set up the partial fraction decomposition, but not solve for these constants. So happily, we can just see, this is how this breaks down. We break it down this way. We use each of the rules based on whether it's linear or it's an irreducible quadratic, and they show up the number of times of each of their exponents. Great. Third example. Find the partial fraction decomposition for x to the fifth plus 3x cubed plus 7x over x to the fourth plus 4x squared plus 4. First thing to notice, it has a degree 5 on top, degree 4 on the bottom, so we start off as improper. So since it's improper, we have to use polynomial division to break it into a format that is proper first. So how many times does x to the fourth plus 4x squared plus 4 go into this thing here? So let's set up our polynomial division. 4x squared plus 4 goes into x to the fifth plus, we have no x to the fourths, plus 3x cubed, we have no x squareds, plus 7x, and we have no constants. Okay, so how many times does x fourth go into x to the fifth? It goes in x, because x times x to the fourth gets us x to the fifth. Then we do it on the other things, plus 4x cubed, plus 4x. So we subtract all this, so let's distribute that subtraction minus, so x to the fifth minus x to the fifth becomes 0, no surprise there. 3x cubed minus 4x cubed becomes negative x cubed. 7x minus 4x becomes positive 3x. We can now bring down everything else, but as soon as we do that, we realize, oh hey, there's nothing else to be done here, because how many times does x to the fourth go into 0x to the fourth? It goes in 0 times, right? It can't fit in at all because it's just a 0 to begin with. So we found our remainder. Our remainder is what remains. Our negative x cubed here are 3x, and that's it. So negative x cubed plus 3x is what remains. So that means that what we originally started with, x to the fifth plus 3x cubed plus 7x all over x to the fourth plus 4x squared plus 4 is equal to, x came out of it, so x plus what our remainder was, negative x cubed plus 3x over that original denominator, x to the fourth plus 4x squared plus 4. Great. Need some more room. Let's flip to the next page. So that's what we figured out. We figured out that what we started with breaks into this thing right here. So now let's figure out how can we decompose this part on the right. We'll work on decomposing this first, but we can't forget, circle it in red so we don't forget, can't forget that x, because that's still part of that function. We can't actually decompose it without putting that back in at the very end. Otherwise, we'll have decomposed a different function. We'll have decomposed this function right here, but forgotten about that, what we originally started with, because what we originally started with includes this x. All right, so negative x cubed plus 3x. Oh, that's one thing I forgot to do. Last time we had x squared plus 4x plus 4. Sorry, x squared plus x to the fourth plus 4x squared plus 4. I quietly factored that without ever mentioning that. It factors into x squared plus 2 squared. Sorry about that. Hopefully that isn't too confusing. Negative x cubed plus 3x over x squared plus 2 squared. So that's going to be equal to ax plus b, because it's an irreducible quadratic, divided by x squared plus 2 plus cx plus d over x squared plus 2 squared. So at this point, we multiply both sides by x squared plus 2 squared, x squared plus 2 squared, x squared plus 2 squared. So that cancels out here, and we're left with negative x cubed plus 3x equals, what happens to ax plus b? Well, its denominator gets canceled, but then it's still left getting hit with one more x squared plus 2. What about cx plus d? Well, its denominator just gets canceled, right? There's nothing left after x squared plus 2 squared hits because its denominator was the same thing. So we're just left with cx plus d. So let's expand that. And let's also put this in a different color just so we don't get confused by the separation. Well, I'm not sure how much that will help us. 3x equals ax times x squared becomes ax cubed. Ax plus 2 becomes 2ax. Bx squared plus 2b. And we'll also bring along plus cx plus d. At this point, we can set things up so we can see it a little more clearly by putting everything together that comes in a single form. So we've got ax cubed. Then we'll leave a blank for the x squareds plus 2ax. And then we can write over here plus bx squared plus 2b. Oh, whoops. Sorry, that's going to have to leave a blank there as well. Plus 2b. And then plus cx. And then plus d. Notice how this works. We've got our cubes here. Degree 3 things here, degree 2 things here. Well, not quite degree because they're not the whole polynomial, but things with exponent 3 here, exponent 2 here, exponent 1 here, exponent 0 here. So now we can compare that over here where we've got exponent 3 here, exponent 1 here. So all of the things that are going to connect to the negative x cubed, which we can also see as negative 1 times x cubed, is just ax cubed here. So it must be that negative 1 is equal to a. Otherwise, we wouldn't have negative x cubed in the end. So we now know negative 1 equals a. Great. What about 2bx squared? Well, we've got 0x squared, right? We know that 0x squared equals bx squared, right? Things of degree 2, well, we could have just written that as 0 equals b because our things of degree 2 has to line up with that number b. So 0 equals b. What about our d here? We can figure out our d. Well, we've got a constant, right, plus 0 here. So it must be that 0 is equal to 2b plus d. Well, we already know b equals 0 here, so that just knocks out. So we're now told that 0 equals d as well. Finally, we're left figuring out what what c is. So we know that 3 here, 3 equals 2a, because there's that many x, because we've got 3x and 2ax and cx. So it must be that 3 equals 2a plus c, right, when we combine them all together. So we plug in numbers. 3 equals 2 times, what is our a? It is negative 1. So negative 1 plus c. So we get 3 equals negative 2 plus c. Or we add 2 to both sides. 5 equals c, right? So 5 equals c. So at this point, we've managed to figure out everything that goes into our decomposition. So we can write that decomposition out, ax plus b. So we've got negative 1 as our a. So negative x, what's our b? Our b is 0, so it just isn't anything. X squared plus 2 plus cx plus d. So our d was 0, our c was 5, so it's going to be 5x over x squared plus 2 squared. And we can't forget that x that was originally there, so x plus that. And that is our entire partial fraction decomposition, breaks down into that guy right there. All right, final example. This one's a rough one, but this is the absolute hardest you'd wind up coming across in class in a test, so don't worry. This is basically a top difficulty you'll have to deal with. Probably. You might see something a little bit harder, but this is really about as hard as it's going to get. All right, so happily, they already factored it for us, and we've got t minus 2 squared, t squared plus 2, so this is degree 2, this is also degree 2, so that combines to degree 4 on the bottom, degree 3 on the top, so we're proper. Our bottom's already factored. We just need to actually work through the decomposition now. So we've got negative t cubed plus 8t squared minus 6t over t minus 2 squared, t squared plus 2. So how does that decompose? A over linear factor of t minus 2 plus b over our second version of that linear factor, so t minus 2 squared, plus cx plus d over our irreducible quadratic factor of t squared plus 2. Great. So at this point, we multiply both sides by the denominator. Multiply both sides by the denominator, and we will get negative t cubed plus 8t squared minus 6t equals a times, so it got hit with t minus 2 squared times t squared plus 2. So it's going to cancel out one of those t minus 2's, and it will be left being multiplied by t minus 2 and t squared plus 2. Plus b, t minus 2 squared was in its denominator, so it's going to cancel out all of the t minus 2 squared that hit it, but not the t squared plus 2 at all. So we've got t squared plus 2. And then finally, plus cx plus d, and it's going to have to go in parentheses because it got hit by another entire thing, and it's going to get t minus 2 squared, but it did cancel out the t squared plus 2 that hit it because it had that in its denominator. So at this point, we want to start simplifying things out. So we've got a times, what is t minus 2 times t squared plus 2? So we get t cubed, t plus 2t, sorry, t times 2 becomes 2t minus 2t squared minus 4, okay, plus bt squared plus 2b, okay, plus cx plus d times t minus 2 squared becomes t squared minus 4t plus 4. All right. Move a little bit to the left so we have more room. Still the same thing on the left side. So we've got at cubed plus, sorry, minus 2a t squared plus 2at minus 4a, whoops, try to switch colors there, plus bt squared plus 2b, break onto a new line now so we can see what's going on. Cx times t squared will become c, made a mistake right from the beginning. It should not be x. It should be, I just stuck with what I've been used to, where a variable that we're dealing with isn't x, it's t here. So that should have been a t the whole time. Sorry about that. But that's the sort of mistake you want to catch on your end too. Because we're dealing with a variable, we're dealing with t as our variable. So while the form was with x's before, that's because the variable was x before, but now we're dealing with t as a variable, so the form needs to switch to using t. So let's work this out. Ct times t squared becomes ct cubed. Ct minus 4t becomes minus 4ct squared. Ct plus 4ct plus dt squared minus 4dt plus 4d. Whew, okay, got a lot of stuff here. So we can say this is negative t cubed plus 8t squared minus 6t equals, and we can put this in that form again of thing of exponent 3, exponent 2, exponent 1, exponent constant, minus 2at squared plus 2at minus 4a. Next one, plus bt squared plus 2b plus ct cubed minus 4ct squared plus 4ct, and then plus dt squared minus 4dt plus 4d. So from this, we'll be able to figure out that all of our t cubes, right, our line of t cubes here has to be the same as our line of t cubes here. So we'll be able to get things like -1 equals a plus c. Now, this is a lot of stuff to have to work through, right? We've got 4 different variables. We're going to wind up having 4 different simultaneous linear equations that we're going to have to solve through. If you've done much work with simultaneous linear equations, you know that's going to be kind of a pain to work through. So at this point, we might think, I'm lazy. Is there anything clever I can do? Is there a clever way to work through this? Some little trick I could use? Well, if we look back to what we originally had when we multiplied out that denominator, we might go, well, oh, hey, look. There's a t minus 2 here. There's a t minus 2 here, but there is an absence of t minus 2 on our b. So if we realize that, we could go, well, if we plug in t equals 2, right, that would cause, now, none of this stuff up here is not going to be true, but we're going to plug in t equals 2, and we're going to realize if we plug in t equals 2, that causes this to turn to 0, which knocks out our a terms. And it will cause this here to turn to 0 as well, and it will also knock out our c and our d terms, and we'll be left with just b times t squared plus 2, where t is 2, only t is 2, and negative t cubed plus 8t squared minus 6t when t is 2. Now, this is true for any t, right? So that means we can plug in any t we want, and if there's a convenient way to get certain things to disappear by plugging in a cleverly chosen t, it's fair game, right? Anything we can do to help us work through this, anything that makes it easier, it's fair game. So in this case, we notice that by plugging in this carefully chosen t, we can get certain things to disappear. Now, it's true for any t. This equation, this whole thing here is true in general for any t before we crossed stuff out. But in the specific case where we plug in t equals 2, certain things will cancel out, and we'll be able to figure things out in a very easy way mathematically. So we plug this in, and we know that on our left side, we're going to have negative 2 cubed plus 8(2) squared minus 6 times 2 equals, sorry, not quite a lot of room here. I'm going to draw in a line just so we don't get confused, equals b times 2 squared plus 2. Okay, so we've got negative 2 cubed is 8, plus 8 times 2 squared is 4, so 32 minus 6 times 2 is 12 minus 12 equals b times 4 plus 2, or 6. Simplify the left side, so negative 8 minus 12, negative 20, 32 minus 20 gets us 12 equals 6b. We divide both sides by 6, and we get 2 equals b. So, by use of some cleverness, we were able to skip having to do 4 simultaneous linear equations to eventually we're effectively going to bring it down to 3. And we'll be able to not have to get confused by this most complicated column where we've got 4 different things all going together. We can just be done with b. B's already figured out, which will be really helpful and make things easier on us down the road. We could have solved out those 4 simultaneous linear equations because each one will produce things. Remember how the first column produced negative 1 equals a plus c. Each one of these columns will produce a equation, and from 4 simultaneous linear equations, solving for 4 variables, we'll be able to do it. It's just kind of a pain. So we came up with this clever way, and we were able to figure out 2 equals b by just happenstance. If we plug in t equals 2, it made everything but the b terms disappear, and that just left us with a single equation that was pretty easy to solve, and we figured out that 2 equals b. All right, let's work through it now. So we figured out b equals 2. And now we've got negative 2 cubed plus 8t squared minus 6t equals at cubed plus ct cubed minus 2at squared plus bt squared minus 4ct squared plus dt squared plus 2at plus 4ct minus 4dt minus 4a plus 2b plus 4d. Hoi. Okay, so at this point, let's put columns to columns. So negative t cubed goes to our at cubed plus ct cubed. So it must be that negative 1 is equal to a plus c. So negative 1 equals a plus c. We can do this column here. I accidentally cut through that negative sign. Hopefully that wasn't too confusing. So that one here lines up with the negative 6t. So we've got that negative 6. Let's write it on a separate location. Negative 6 equals 2a plus 4c minus 4d, right? They've all got t's showing up, so we just divide out the t's, and we're left with this simple, linear equation we can work with. And then finally, the last one of constants. Well, what's our constant? Our constant is 0. So we've got 0 equals negative 4a plus 2b plus 4d. For extra credit, let's just see what this would have been. How many t squareds do we have? We had 8. So in our difficult to read yellow, I'll make it black just because black's easier to read. 8 equals negative 2a plus b minus 4c plus d. We could have worked that one out, but I want you to see what it would have been, but we'll actually wind up having enough information because we've got 3 equations, 3 unknowns, so we've got enough with the red, blue, and green things. So at this point, let's figure out a first. So that means we need to solve for everybody who isn't a so that we can plug them in, get rid of everybody else, and just have a. So on the left side, we've got negative 1 equals a plus c. So we solve for c, and we get negative a minus 1 equals c. OK. On the green one, we plug in what we know for our b. We've got 0 equals negative 4a plus 2 times 2 plus 4d. 0 equals negative 4a plus 4 plus 4d. 0 equals, let's divide everything by 4 just to make things easier, negative a plus 1 plus d. So we move that stuff over, and we get add a on both sides, subtract by 1 on both sides, a minus 1 equals d. So we've got a minus 1 equals d. We've got negative a minus 1 equals c, so we can plug this information in to this equation, and we'll be able to get something that is just using a. Negative 6 equals 2 times a. That guy actually sticks around because he was just a from the beginning. 4, what did we figure out c was? C is the same thing as negative a minus 1. Negative a minus 1 minus 4 times, what do we figure out d is? Same thing as a minus 1. Simplify that out. Negative 6 equals 2a plus 4 times negative a, so we'll make that minus 4a minus 4, negative 4a minus 4a, and negative 4 times negative 1 becomes plus 4. So at this point, we see we've got negative 4 and plus 4, so those cancel each other out. We've got negative 6 equals 2a minus 8a, negative 6 equals negative 6a, and thus 1, divide both sides by negative 6, equals a. With 1 equals a in place, we can now easily go back and figure out everything else. So we've got negative a minus 1, so negative, plug in our knowing that it's 1, minus 1 equals c. So we've got negative 2 equals c. Great. And also plug in over here, and we've got that 1 minus 1 equals d. Turns out d is just 0. So at this point, we've figured out all the things we need. So we had this set up as t minus 2 and plus t minus 2 squared plus t squared plus 2, right? It was in the format negative, it was in the format negative t cubed plus 8t squared minus 6t all over t minus 2 squared times t squared minus plus 2. Okay, so that's the case. We had that as something over t minus 2. It was a over t minus 2 plus b over t minus 2 squared plus cx plus d, right? Cx plus d over t squared plus 2. Okay, so at this point, we can actually plug in our numbers. So we've got a is 1, so we've got 1 t minus 2. B is 2, so we've got 2 t minus 2 squared, plus c was negative 2, so minus 2x, and 0 was d, so that part just disappears. So we've got negative 2x over t squared plus 2. Whoops. Once again, did it again. Got thinking in terms of x as opposed to t, but we're using a different variable, negative 2t over t squared plus 2. And there we are. We've decomposed it into its partial fractions. That is pretty long, it's pretty complicated, but that's pretty much as hard as it gets. As long as you break it down and then you multiply everything out carefully and you're careful with all of your algebra and your arithmetic, you can get it into this form right here where you've got this big block compared to these original things, and then you're able to figure out all these linear equations, and you can possibly be clever and have her figure out some way to get, b equals 2, but you also can just work through a bunch of linear equations, solving for one thing at a time in terms of the other, plugging them all together, and then solving it out. Sometimes it takes a lot of work, sometimes it goes kind of slowly, but ultimately if you just keep plugging away at it, you can get it. And it's really, really useful in calculus. I know you aren't going to be using it immediately, but honestly, this thing makes a problem that would be otherwise totally impossible to do just a piece of cake. So it's a really handy thing in calculus. All right, we'll see you at educator.com later. Bye.